All right, in this example, we're told we have some brine, just salt water, passing through an 85% efficient pump. And we're given the flow rates, 125 liters per second. The center lines of the pump's 300 millimeter diameter inlet and 200 millimeter diameter outlet. So that just means the diameter of the inlet and outlet lines are at the same elevation. So these are at the same elevation there. The inlet suction gauge pressure is 150 millimeters of mercury below atmospheric pressure. So that's the pressure right here at the suction side. The suction side is the inlet side. And the discharge pressure is measured at 1.2 meters above the, right there, 1.2 meters above the center line of the pump's outlet. So that distance is 1.2 meters. And it indicates 138 kilopascals gauge pressure. So neglecting losses in the pipes, what is the input power into the pump? So we want to know what kind of power is going into the pump. All right, so in order to determine the input power into the pump, what I'm going to do is, when I look at this, I know the efficiency of the pump, so we're told that, and I also can determine the power going into the fluid because I know the pressure rise into the fluid, and from that pressure rise I should be able to figure out the head rise that goes into the fluid, and if I know the head rise into the fluid, I can find the power that's going into the fluid, and if I know the power into the fluid and the efficiency, I can get the power into the pump. So let me just go ahead and sketch this out for you, the procedure I'm thinking of. So the efficiency of the pump will be the power that goes into the fluid divided by the power that gets into the pump, or that you put into the pump. So obviously the power into the pump is the power into the fluid divided by the efficiency of the pump. So I'm given the efficiency of the pump, that's right there, 85% efficiency. So I need to find the power that gets into the fluid. Well, I know that the head rise is related to the power that gets into the fluid. So the head rise across the pump is the power that goes into the fluid divided by the mass flow rate times gravity. And I could, of course, write the mass flow rate as the density times the volumetric flow rate. So I could rearrange this to write the power that gets into the fluid is the density times the volumetric flow rate times gravity times the head rise across the pump. Now the head rise across the pump we can figure out because we're given information about the pressure increase across the pump as well as some information about the flow rate and elevation changes. Okay, so if you think about applying the extended Bernoulli equation from this point to that point, let me just put the numbers on there. Oops, we'll do it in blue. So we'll have point 1 here and point 2 there, and we'll apply the extended Bernoulli equation between those points. So here's the extended Bernoulli equation between those 2 points. We're told to neglect losses in the pipes and such, so we're going to neglect that, so that'll be, the head loss will be 0. We know the pressure at 1, that's given, that's the minus 150 millimeters of mercury gauge. So obviously there's a unit conversion there that we'll have to make. And then the outlet pressure is 138 kilopascals gauge. We know the velocity at 1 will be the volumetric flow rate through the pump, which we're given. The volumetric flow rate is given up here is 125 liters per second, so we know that. So if we divide that volumetric flow rate by the area of the first pipe, we can find V1. And we know that the diameter of that first pipe is 300 millimeters, so we have that. We can do the same thing at location 2. It's the same volumetric flow rate divided by the area of the pipe there. Again, we know the area of the pipe there, it's 200 millimeters, so we can find that area. It's the same volumetric flow rate that was given in the problem statement. And then we also know the elevation difference. Z2 minus Z1 is the 1.2 meters. That's this height right here. So we can rearrange that equation. I guess the other thing that we should assume here is that alpha 1 and alpha 2 are equal to 1. We're assuming it's turbulent. And although I guess I haven't checked the Reynolds number to verify, I'm pretty confident that it's going to be turbulent. In fact, because the diameter of these pipes is pretty large, and the velocity that you'll find after you do this calculation is actually pretty significant as well. So the Reynolds numbers are going to be large. It's a very reasonable assumption to assume that this is a turbulent flow. So if you go through and plug in the numbers as well as the doing the unit conversions, you'll find that the head rise across the pump is 15.3 meters. And then once you have that, you can find the power into the fluid. That comes out to be 22.5 kilowatts. And then using the efficiency that we're given, we can find the power that we have to put into the pump. And that comes out to be 26.4 kilowatts. Okay, so just to kind of recap what we did here, we were trying to find the power that we have to put into the pump. And the way I found that was I sort of worked backwards. I know that since I'm given the efficiency of the pump, I know the efficiency is related to the power that goes into the fluid divided by the power into the pump, so I could rearrange that. The power that goes into the fluid I know is related to the head rise that goes into the fluid. It's just the head rise is just another way to write the power or energy that gets into the fluid. So I just rewrote the power that goes into the fluid in terms of the mass flow rate, gravity, and the head rise. And the head rise I can find from the extended Bernoulli equation. And I knew that I could find it from there because I know the pressures at points 1 and 2, I know the elevation, and I knew I could find the velocity because I'm given the volumetric flow rate and the pipe diameters, so I could get the velocities from that. So that's how we find the power into the pump. By the way, let me just give you some intermediate values, just in case you work out the numbers yourself, you can check. The velocity in pipe 1 is 3.98 meters per second. The velocity in pipe 2 is 1.77 meters per second. So that just gives you some intermediate value. And the pressure at the inlet, so at 1, where it's given in millimeters of mercury, that comes out to be minus 20 kilopascals gauge. So if you do that unit conversion, you can just check yourself there. All right, that's it for this example. We'll end it there.